trying to figure out what happened to that O2 tank too.
Right. Now our pressure still should be good. And you see we got our low point.
Why did the temperature drop so suddenly?
Because it probably don't have anything left in it.
Yeah. And we're losing tank 1, if we can believe it.
Losing what?
Tank 1 pressure.
Yeah. No heat recycle. I can believe it.
Well,
and it's the only one on the line now. If tank 2's failed. It's going down. It's been going down. Third tank slowed down.
We blew the manifold?
It looks pretty good that we blew it between the check valve and O2 tank 2. In other words, I don't think O2 tank 1 is affected. Other than it doesn't get any heat recycles right now to boost the pressure up. I'm hoping that's right.
Well, I hate to go manual heat, wouldn't you?
Good evening, everybody. Owen Brown, and it's a pleasure to be with you tonight here on the 50th anniversary today of the successful return and splashdown of Apollo 13. This mission's been a very special story for me to tell for the last 25 years. 1994, I started to give a presentation while working at Space Systems Loral on Apollo 13, and at the time the only resources I had were NASA Ames Library, the library down at Johnson Space Center. Thanks to them for a lot of audio and video that you're going to see tonight that was developed and placed into the presentation. And then at the time, that thing called the World Wide Web, which had just started to be a real tool for research. But over time, next 6 months or so, Jim Lovell's book comes out, and then the movie shortly thereafter, and then a great deal of interest developed with this message and this story that I've given probably about 100 times. So once again tonight, very special opportunity as we remember the courage and technical excellence of the Apollo 13 crew and all the steely-eyed missile men down at Mission Control in Houston. So let's get rolling here. So here's the outline of tonight's discussion that I've given once again many times. First of all, I'm going to answer what. Undoubtedly, many of you, if not most of you, have seen the movie. And tonight, in fact, you'll probably catch me saying, you'll remember from the movie. And when I say you'll remember from the movie, what I really mean is you should remember from the mission, because the movie is so technically accurate. Ron Howard did such an awesome job with the Apollo 13 movie and describing the events beginning on April the 13th, 1970, and then culminating the successful return of the mission. So, using the movie as reference as well as actual audio tape, we're going to talk about exactly what happened, what was going on in the Apollo command and service module systems at the time of the failure. As you know, the crew within 2 hours had to climb, 2 hours of the failure has to climb over into the lunar module and use it as a lifeboat. Immediately you start thinking about consumables, especially things like oxygen and power, and oh my goodness, are they gonna have enough to get back? So we're gonna talk about those consumables, the uses the LEM as not only a lifeboat but a powerboat, and describe just how close those consumables came to running out. Then finally, now this is the part of the talk when I'm giving it after a dinner that as I'm giving it, I can look out into the audience and I can see everyone's mouth is wide open. And that's because of one of two reasons. Either one, they're totally aghast with the reason that this tank failed and it was doomed to fail. Or two, they've fallen asleep. So I beg of you, do not fall asleep. Do not be asleep or go to Netflix when I get to this part of the presentation, because it is absolutely the best part of the presentation. It is indeed the rest of the story. So let's get going and talk a little bit first and establish some context. Once again, very well portrayed and described in Ron Howard's film. So here is the original flight crew of Apollo 13. Very much a Department of Navy strong flight crew. You have Captain Jim Lovell, Lieutenant Commander Ken Mattingly, and veteran Marine flyer Fred Hayes. Now, just a mere 3 days prior to launch, turns out, once again, as you remember from the film, Ken Mattingly is bumped from the mission because the entire crew, in fact, has been around backup crew member Charlie Duke, who has contracted the German measles, rubella, from his kids. Lovell and Hayes, both immune because they've had it as children. Mattingly has not, and under the strenuous objections of Jim Lovell, Ken Mattingly is bumped from the mission, later to go on and fly, in fact, with Charlie Duke on a very successful Apollo 16 mission along with John Young. Ken Mattingly, of course, replaced by Jack Swigert. So here we have the Apollo 13 crew. Let's talk about that crew for a minute. Two space rookies, Hayes and Swigert, a astronaut, Jim Lovell, with at the time the most experience, the most time in space. 30 days total on lengthy Gemini missions, a Apollo 8 mission circling the moon on Christmas of 1968, and a very, very experienced astronaut. Now, Hayes and Swigert, like I said, space rookies, but turns out that Fred Hayes is, in his spare time, the astronaut rep at the Grumman facility, which builds the lunar module. Fred Hayes is the lunar module pilot. Jack Swigert has an identical type of job as the astronaut rep at the North American plant out in Downey, California. for the command and service module. That's where the command and service module is built. So you have two astronauts who know those systems in and out, and an incredibly experienced commander. So if you're going to have to pick a crew to be on this mission, which is doomed in the end for failure, this would be the crew, in my opinion. So, launch of Apollo 13 from Pad 39 of Cape Canaveral goes off without incident. Now, if you look up on that day, on April 11th, 1970, at the clock, the Johnson Space Center, the time reads 13:13. And then we go back to Pad 39, which happens to be the third multiple of 13, and you begin to wonder what exactly a numerologist would think might become of this mission. So, we're going to talk a great deal about these two spacecraft that you see here. Command and service module and the lunar module. So it's important that we understand contextually what they're designed to do and how long they are actually meant to last. So we see over here on the left the command and service module named Odyssey. It is the living quarters here in this conical section, the command module for three crew members on and off, as designed in this mission for about 10 days. Apollo 13 takes off on April 11th, and it is designed to return on April the 21st. So most of the time, 3 men, 3 astronauts in the conical section. This cylindrical section, that is the service module. Not a living space, but a space for propellants, for the rocket engine down here at the bottom that you see, the service propulsion system engine, reaction control system, thrusters, as well as housing the cryogenics, hydrogen, and oxygen, which we're going to talk a great deal about. Now, the lunar module, Aquarius, meant to take Lovell and Hayes to the moon for a period of about 30-odd hours. 30-odd hours to go to the lunar surface. Here we have the descent propulsion system engine, which will break the spacecraft out of lunar orbit, be used to land on the moon. Living quarters up here, hatch here, and after their 2 planned lunar excursions, lasting about 30 hours, this section, upper section, the ascent stage, will lift off. There's yet another rocket engine down here. So, at maximum, this lunar module designed to hold 2 men for 2 days. So, all has gone well. We find ourselves on the night of April the 13th, 1970, some 205,000 miles from Earth, heading towards the moon, about 2,000 miles per hour relative to the moon. The crew has provided a television broadcast, which none of the networks at the time decide to pick up. And they button up and began to stow their equipment. That is when the problem takes place. So let's listen to some of that actual audio tape.
Okay, Houston, we've had a problem here. This is Houston. Say again, please. Houston, we've had a problem. We've had a main B bus undervolt. Roger, main B undervolt.
A main B undervolt. So up in the center section of the command module main control panel, indications and warning area, appears this main B undervolt alarm. Now, between mission control and the spacecraft, there are 50 odd coincident alarms and anomalous indications. So let's talk about what a main bus B undervolt is. It's really the first symptom that appears, but to understand that main bus B undervolt really begins to understand the exact problem that was affecting the spacecraft. So what we're going to do is dive in to a little bit of technical detail on the Apollo electrical distribution system. So here we go. Here's a diagram that will explain everything. But don't panic. This is not what we're going to use. But if you want a command and service module to check out later, you need to know by heart and be able to draw this on the whiteboard. We're going to simplify this diagram to something technically correct to get down to the basics. So we have here a diagram which everything in the blue area is in that conical command module. Above that black line, in that blue area, everything will be in that conical command module. Everything in the orangish yellow, and it's labeled there SM, is in the cylindrical service module. In the command module, we have two main buses. These buses, a bus is essentially an electrical distribution center. And you have two buses. It's just their philosophy for providing redundancy and reliability. If one fails, the other one can pick up the load. The same type of philosophy exists for other spacecraft, satellites, submarines, and ships, etc. The power coming off of those main buses is typical spacecraft power at plus 28 volts DC. Now, the source of power is found down in the service module from 3 fuel cells. We're going to talk a lot more in detail about fuel cells. We could connect fuel cells to buses with a switch lineup. In the case of that night on Apollo 13, so it happened that fuel cell 1 and 2 are powering main bus A, and fuel cell 3 is powering main bus B. Now, a little bit more. There's a lot of equipment, computers, navigation equipment, indications equipment for tank quantities, etc. That requires 115 volt AC power, essentially the power coming out of the voltage coming out of your wall plug. And that's created through conversion using these two inverters off of those main buses. Now, there are also 3 batteries in the command module. 3 silver oxide zinc batteries that can provide power to either main bus A and or main bus B. The purpose of these batteries, just prior to re-entry, the service module will be released. A guillotine device will sever mechanical and electrical connections, and therefore there needs to be a source of power in the command module. That source of power for a period of about an hour comes from these batteries. So if the fuel cells would happen to go away and fail, those batteries are only going to function for a period of about an hour at maximum discharge rate. Not going to help you 200,000 miles from Earth. So, a main bus B undervolt is an indication that there has been a lowered voltage on main bus B. We'll talk a little bit more about exactly why that main bus B voltage goes down, but that's what a main bus B undervolt alarm means. We're losing voltage on that main bus. So you listen to the flight loop, and I and my other space nerd friends have been listening for the last several days to Apollo 13 in real time, and one of the first things you hear on that loop after this event happens out from Psi Libergat is, "We may have had an instrumentation problem, flight." Because once again, 50 coincident alarms and indications just does not stack up. There doesn't seem to be a common root cause to all those indications and alarms. But pretty quickly, it becomes readily apparent that this is not an instrumentation problem. Jim Lovell starts to do what any good pilot would do, and that is inspect his spaceship. And he begins to find things.
Jack, our O2 quantity number 2 tank is refilled. Don't forget that. O2 quantity number 2 is 0. Can I look today looking out the hatch that we are venting something? We are venting something out into space. Roger, we copy your venting. It's a gas of some sort.
Now, at this point, up to this point, Jim Lovell has been very concerned about the fact that the lunar mission could be scrubbed. And he's later said that now this is the point in the mission when that becomes an afterthought. And what he's really concerned about is making it back to Earth alive. So, last few minutes, and if you reflect back to the recreation in the movie, just prior to that main bus B undervolt, there's a bang, there's a spacecraft control problem, turns out in pitch and roll, little exaggerated in the movie, but nonetheless there is a control problem. We get the main bus B undervolt. There are indications of an empty oxygen tank. Number 2, Jim Lovell sees a venting gas. And in the movie, there's this great scene where Clint Howard, Ron Howard's brother, who's playing Psi Libergat, has a discussion with Ed Harris playing Gene Kranz. And the conversation goes, "Flight, I recommend we shut down the reactant valves to the fuel cells. If that's where the leak is, we can isolate it and we can use what's in the good tank and run on the good cell." And then Ed Harris says, "Si, you close them, you can't open them again." So they're trying to isolate these fuel cells, which appear to be failed. So let's talk about fuel cells and some of these other issues and oxygen tanks. And we're going to now dig into bay number 4 in the service module and we're going to do a little bit of technical deep dive on the cryogenic storage systems. Once again, complex system. This is just for the oxygen portion, but we're going to simplify. That cryogenic system, the key chemical reaction that is part of that cryogenic system is right here. Some simple high school chemistry. You mix hydrogen with oxygen, this exothermic reaction. The reactants are water and, of course, energy. So that oxygen, in addition to being used for now producing, as it turns out, power, is used for breathing supply. The water goes to a potable water tank on board, and that's used for drinking. And the energy, that's the electricity. That's the main purpose of hydrogen and oxygen cryogenically stored. That reaction takes place in each one of the fuel cells. I show connections here for fuel cell 1, but the same ones can exist for fuel cells 2 and 3. So you see, we have hydrogen going in, oxygen going into the fuel cell, and comes out water and flowing electrons, the power. Now what we're going to do is focus on the oxygen portion of the cryogenic systems. The hydrogen portion is nearly identical. So here's that oxygen portion of cryogenic storage. See, we have 2 oxygen tanks, number 1 and number 2. Once again, 2 for the purposes of redundancy. 1 tank is more than enough to get astronauts to the moon and back, although a loss of a tank would scrub the mission. But 2 there in case something would happen with 1 tank. We have connections then that go to the environmental control system. That is where we're going to regulate this oxygen down to a pressure for 5 pounds per square inch in the command module for breathing. Flow through 2 check valves here. And the purpose of those check valves is to ensure that if I have a problem, let's say I start to lose oxygen here, this oxygen is not going to flow in that direction to the hole. So both tanks then meet at a manifold and then flow to each one of the fuel cells. And here are those reactant valves. And those reactant valves are there for purposes of fault isolation. In case there's a failure, a leak, for example, in a fuel cell, you can shut those reactant valves. They're electric solenoid valves. But just like in the movie, once you shut them, you can't open them again. You need ground support equipment to open them back up. So that is, once again, those valves for purposes of emergency isolation. Let's look in to the bay here at the actual close-out photos inside of Apollo 13 of those various components. So you see, here are the oxygen tanks. There's number 2. Turns out to be the culprit in all of this. Below there are hydrogen tanks. By the way, you can see we're looking inside of here for scale. So this is about 2 feet right here, 2 feet in diameter. Up here are the fuel cells. Number 3, number 1, number 2 is in the back here. So that's the general layout. Now, what had happened? It took a little bit of time to figure this out. There had been an event in oxygen tank number 2 that resulted in a failure of that tank, a catastrophic failure. I hesitate to say explosion, because we'll see why later. that resulted in the almost immediate expulsion of the contents of oxygen tank number 2. That expulsion of oxygen pressurizes bay number 4, blows off the bay door. There's a temporary point where they've actually been able to determine, based on temperature readings, that before the bay door blows off, mylar insulation actually catches on fire. That event, combined with the bay door being blown off, that is the bang. And then this venting gas from that tank is a propulsive jet that results in those spacecraft control problems. Now, this situation, as it's shown right now, is not lunar mission ready, i.e. you're not going to land on the moon in this condition now, but it's not life-threatening to the mission, because we've got 1 healthy oxygen tank and 3 healthy fuel cells. But a couple other bad things happen. The reactant valves are located very close to the oxygen tanks. That G-load caused by the expulsion of oxygen out of this tank impacts the shelf on which these reactant valves rest and mechanically slams them shut. The result, within the period of about 2 to 3 minutes, is that fuel cells 1 and 3 are starved of oxygen and therefore turn off, leaving only oxygen tank number 1 and fuel cell 2 to provide power to the command module. Now, let's go back and reflect to what was happening in the mission. Well, remember, I said it's very technically accurate that mission control wants to shut the reactant valves. In reality, they don't want to shut them both at the same time. They try to isolate one at a time, but in any event, they want to shut those reactant valves. And now, wait a minute, I'm telling you, those reactant valves are shut. That's part of the problem that we're in the failure here, is they've been mechanically slammed shut. Why are they telling the crew to shut reactant valves, the fuel cells 1 and 3, when they're shut? And that's the reason fuel cell 1 and 3 have failed. Not that there's a leak in fuel cell 1 and 3. Well, remember, there's also a hydrogen system here. With that hydrogen system also has reactant valves. Those reactant valves are located in a different place in the bay, in service module bay number 4. They're in a different location. They remain open. It turns out that the voting logic inside the command module for the indications and warning requires, for a shut indication for a reactant valve, both the oxygen reactant valve and the hydrogen reactant valve have to be shut. In this case, only the oxygen reactant valves were shut, hydrogen valves open, so therefore, as far as everyone else is concerned, the reactant valves are open, but in reality, the hydrogen or the oxygen reactant valves are shut. Now, this is bad, but not dire. 1 healthy oxygen tank, number 1. 1 healthy fuel cell, number 2. But one other bad thing happens. Now, it's not completely clear because the service module returned to Earth and burned up, so we don't have it. We didn't have it to go back and look into in terms of trying to find out what happened, but surmise that there was either damage caused by the event over here to oxygen tank number 1, maybe on a pressure probe area, or this check valve here actually allow backflow through the system. And in any event, this tank begins to lose oxygen at a rate that it's going to be empty in about 2 hours. So let's talk about the scale of this loss of oxygen out of oxygen tank number 2. Down at Johnson Space Center, on top of a building, there are a couple guys with a 16-inch telescope tracking, watching the last stage, the S4B stage of the Saturn V tumble to the moon. This is 200,000 miles away. They're watching this stage as it's actually, the sun is glinting off of that stage, providing the ability for these guys to watch it through the telescope. They capture here on a video screen capture not only the command and service module that you see there, but an oxygen cloud reflecting sunlight some 25 miles in diameter. So this is soon after the failure, over 200,000 miles away. Okay, so that gives you a sense of what was going on that night on April the 13th. Of course, 2 hours of oxygen left in that tank means 2 hours of power left in the command module. There's no other recourse but to pile into the lunar module and use it not only as a lifeboat, but you can see here in this artist depiction, the synpropulsion system engine is being utilized. It is being used as a powerboat, a source of propulsion necessary to correct the trajectory of the orbit to get the astronauts back safely to Earth. So let's talk about some of the natural questions that start coming about. Remember, 2 men, 2 days. 3 men versus 3 men, 10 days. Is there going to be enough oxygen in the LEM? Is there going to be enough water in the LEM? Well, here is a history of the oxygen contents remaining in the lunar module beginning right around the time of the problem at 55 hours. So you can see that this comes down at a fairly steady rate. I mean, after all, oxygen, it's hard to conserve oxygen. You're not going to breathe less coming back. Fairly steady rate, but in the end, 28 pounds remaining in the lunar module. That's over half the original inventory. You must be thinking that 2 men, 2 days, 3 men, 10 days, this doesn't add up. Well, let's talk about the original mission design. Lovell and Hayes are going to land on the moon, and they're going to make 2 separate lunar excursions. Each time you get out of that spacecraft, you put on a spacesuit, you fully depressurize the ascent stage. Otherwise, you can't open the door. You walk out, perform your lunar science, go back in, fully pressurize the spacecraft, take the spacesuit off, eat the hot dogs, and then you repeat that one more time. Depressurize and repressurize. It's through those 2 cycles of depressurization and repressurization that requires much more oxygen for 2 men in 2 days than breathing oxygen for that period from the events of going from Monday night to Friday actually using that oxygen in the recovery phase. Power, that's a little bit closer. Now, the lunar module does not have fuel cells. That was considered early on, but that idea was thrown out in preference for actually putting in batteries. Those batteries made by the fine Eagle Pitcher company out of Joplin, Missouri. Got to give this talk one time down there. That was fascinating. Here we see the power plot, amp hours remaining in the batteries in the LEM as a function of time. And you can see a couple of changes in the slope of this curve. First one right about here. This is, soon going to talk about a PC plus 2 burn that's 2 hours after closest approach to the moon. Right after that burn, when navigation equipment can be shut down, just about everything in the lunar module is turned off, except for the communications radio and a pump that pumps coolant past that radio to make sure it doesn't overheat. Then down fairly continuously, and then right here, the lunar module is used to power up the command module just prior to re-entry. Now, at this point, at that rate, there are about 5 hours of power remaining in the batteries. So, pretty close. Of course, you turn off all this equipment, the temperature in the spacecrafts begins to get very cold. Here in the command module, below 38 degrees. Lunar module, a little warmer in the 50s, but no doubt very, very uncomfortable, hard to sleep, etc. It's like living in a refrigerator for several days. Water. Now, water is used not only for drinking, so that was conserved. So each astronaut was limited to about 6 ounces per day. This resulted in Fred Hayes actually getting sick, getting an infection that forced him some recovery time when he got back to Earth. Water, though, is used as a coolant in the lunar module. So glycol is circulated around the electronics equipment. That heat from that glycol is then removed from water that evaporates from a frozen state into space. So the water curve pretty much follows the power production curve because they're very clearly linked. Okay, another issue in the spacecraft is buildup of carbon dioxide. Now, the way you eliminate carbon dioxide, which every time we exhale, out comes the carbon dioxide, that can become deadly. So the way that you remove that carbon dioxide from the system, any shipmates out there, it's exactly the same way we do it on the boat with lithium hydroxide canisters. You suck air over those lithium hydroxide canisters, they absorb carbon dioxide. After a certain amount of time, they can absorb no more carbon dioxide and have to be replaced. As it turns out, in the lunar module, which is now where the ventilation system is, lunar module built by Grumman takes cylindrical or round canisters. They're not enough for the return to Earth. There are plenty of squarish canisters in the command module. So there is this device that is jerry-rigged using a variety of astronaut parts with directions read up directly from Ken Mattingly to the crew without the aid of email or JPEG pictures or anything like that, voice only, and built this contraption. So just like in the Navy, when you go on a very long deployment, take plenty of duct tape. Thank goodness they did. All right, now to the powerboat portion of this. So let's talk about what was a typical trajectory profile for an Apollo mission. So after being placed into Earth orbit on the Saturn IV-B, S4B, a TLI burn is performed. A translunar insertion burn takes you out of that circular orbit and directs you to the moon. Once again, using that Saturn IV or S4B stage. Now, on Apollo 8, Apollo 10, and Apollo 11, the next burn that is performed is this lunar orbit insertion burn. And that burn is performed to place the spacecraft into a lunar orbit. Turns out, I never knew this until today. I don't know why I didn't check, but the lunar orbit insertion burn on Apollo 13 was going to place the spacecraft into a 7, I think by 57 nautical mile orbit around the moon. So at perigee, 7 miles, only 7 miles from the lunar surface. That quite unique orbit that was going to save some propellant, delta V, on the lunar module. Now, given that profile, a TLI burn with nothing else, with no other burns until we get to that LOI burn. If we don't do the LOI burn, what happens? The spacecraft actually is captured by lunar gravity, flung around, and is sent back to Earth in what is known here as a free return trajectory. Now, it may not be necessarily in that fine corridor required for proper reentry. It may be too steep and burning up, too shallow and skipping out. But nonetheless, you're going to come back to Earth in a free return trajectory. Now, in Apollo 12 and now in Apollo 13, those spacecraft were not going to be in a free return trajectory long, because soon after the TLI burn, another burn called a hybrid trajectory burn was performed. In the case of Apollo 13, the purpose of this was to get the spacecraft to the moon so that the timing was consistent with a LEM landing in which the shadows off the Fra Mauro highlands were sufficient that Jim Lovell could properly judge his altitude. So what happens if you're in this hybrid trajectory after that hybrid trajectory burn and you don't perform the LOI burn? Do you come back to the Earth? The answer is no. Now, all the books say, Jim Lovell's book, Andy Chaikin's book, you miss it by some 50,000 miles. And that was a number that had been out there for some time, of 50,000 miles that you're going to miss the Earth. And the story also went then, you're going to go into this long orbit forever, and in Jim Lovell's words, become a permanent monument to the space program. So let's talk about what has to happen now with the lunar module. So the first thing that's going to happen here, after we get the problem, we got to get back in that free return trajectory. We can't be in that hybrid return trajectory. So there is a burn performed using the lunar module only just less than 6 hours after the problem. That gets them back into the free return. Next, we have to get back to Earth a little bit sooner. And so we're going to perform this burn after passing 2 hours after passing the closest point of approach here. Percynthion, a PC +2 burn to get us back 10 hours earlier. And then we need to get ourselves in that fine reentry corridor, and that's the purpose of these mid-course corrections. At the time, nobody knew why the trajectory kept on getting thrown off that perfect reentry, and turns out that, remember that lunar module cooling system using evaporative water? That was actually acting as a small rocket engine, throwing the trajectory off a bit. Now, let's talk about a really cool, this is an astrodynamics cold case for sure. So, very good people at AGI, developers of Systems Toolkit, previously known as Satellite Toolkit, began to do some research and wanted to use their simulation software basically recreate the trajectory of Apollo 13. It was a combination of history and science. A really cool project. And as they did this, and they started to look at that hybrid trajectory, those hybrid trajectory results, some things did not add up. And so, thanks to Paul Graziani at AGI, CEO there, for giving me permission to show this. Clip coming up here, narrated by Andy Chaikin, who, by the way, helped me immensely this past week, providing some information for questions I had. So let's look at what the facts were and the results.
You don't have to be a space freak to know the story of Apollo 13. Chances are you saw Ron Howard's 1995 film, which told the story to the world. You know that astronaut Jim Lovell and his crew had to abort their trip to the moon when an oxygen tank exploded 200,000 miles from Earth. You may remember the men had to use their lunar lander's rocket engine to get back onto the proper course for Earth. And you know what would have happened if the astronauts had failed. They would have missed the Earth and died a lonely death in space when their oxygen ran out. Even more chilling, their bodies would never have returned because Apollo 13 would have circled in space forever. Or so I always thought. It's the story in just about every published account of Apollo 13, including my own book, A Man on the Moon. And it's what I still believed in early 2000 when I asked Analytical Graphics to create some simulations of key moments from the flight. A few weeks later, I got a call from Bob Hall, one of the technical experts there, telling me that something strange had come up. Hall and his team had been working on a simulation showing what would have happened if the astronauts had failed to get back on course. In the simulation, Apollo 13 misses the Earth as expected. But instead of missing it by 40,000 miles, the number that's in all the books, the spacecraft comes much closer, only about 2,500 miles. Then it follows a new orbit that stretches 350,000 miles out into space before it falls back toward Earth again. At first, it looks as if the old story is still correct. But then comes the really big surprise. In the simulation, the spacecraft passes about 30,000 miles from the moon, close enough for the moon's gravity to change its orbit. Now, when Apollo 13 heads back toward Earth, it's on a collision course. On May 20th, 1970, 5 weeks after the explosion, Apollo 13 plunges into the atmosphere and burns up. I was just as startled to hear this as Bob Hall was. We both wanted some kind of confirmation. So I put him in touch with Chuck Dietrich, a flight controller who helped get the Apollo 13 astronauts home. Dietrich went digging into his own files from 30 years earlier, and he found data that confirmed the simulation was right. Of course, Jim Lovell and his crew did get back home safely, and Apollo 13 is a reminder to all of us what people can accomplish when they work together and refuse to fail. I still think it's a story that will be as exciting 100 years from now as it is today. And now it's even more interesting than it was before. I'm Andrew Chaikin, author of A Man on the Moon.
So, pretty incredible work. So, let's talk a little bit about some good old American competition, industrial competition. Some of those engineers at Grumman, after the mission was over, realized that, their lunar module had in fact been used as a lifeboat, a powerboat, and so they thought those guys at North American owed them a little money for that towing expense, and so they wrote up this little bill that you see here, and it does include the battery charge, little accommodations, and it came out to some $312,000. So pretty humorous. Here's the reentry profile of Apollo 13. So coming back, all 3 spacecraft together, the first thing you see there that takes place is service module jettison. Offers a view of the service module for the very first time to the astronauts. Then lunar module jettison, all 3 spacecraft return. The command module, of course, with the astronauts, and then service module, lunar module burning up upon reentry. Now, a couple things about, first, that lunar module reentry. Remember I talked about that S4B stage being tracked by the guys down at JSC with the telescope? It's heading to the moon, and it's going to crash on purpose onto the lunar surface for the purpose of a seismic experiment. And here is the actual reading of the moonquake that took place when that booster hits the moon. Now, the seismometer for that reading was left by Apollo 12 using the Apollo Lunar Science Experimental Package, or the ALSEP package. So you see out here with the Mylar, this is sort of the base station, and a variety of wires that connect to all of the experiments, including that passive seismology experiment. Later missions would fly an active seismology experiment that actually included a mortar and grenades, believe it or not. But here you see Alan Bean preparing the power source for that ALSEP experiment on Apollo 12. He's pulling out a radioisotopic generator cask filled with 38,000 curies of plutonium-238, which are going to power that experiment. So, a similar cask with the same amount of plutonium is in the Apollo 13 lunar module descent stage. So, not only is it a concern for the reentry profile to get the astronauts back where the recovery forces are at, but it's also a concern of where that lunar module is going to land. As it turns out, part of the reentry profile made sure of this. It landed in very, very deep water in the Tonga Trench. That cask covered with carbon covering was designed to successfully endure a launch failure. So there was a lot of monitoring of radioactivity, and none picked up. Once again, I said there's that view of the service module. Jim Lovell's response was there's one whole side of that spacecraft missing. So later turned out that these pictures were very, very helpful. So bay door blown completely off. A lot of just completely jumbled plumbing right here. A high gain antenna, kind of hard to see here, bent backwards. A stain on the nozzle bell of the service propulsion system engine. So, a successful recovery, splashdown, and pick up by the crew of the USS Iwo Jima. Very exciting to listen to that today. Some celebration in mission control. And that was the end. Well, at least was the end of the movie. By the way, once you go out there after this is over and Google Apollo 13 Tom Hanks Jim Lovell scene. Up there on that video screen in mission control, you can see the scene that Ron Howard recreated. And the Navy captain in the movie happens to be none other than the real Jim Lovell. So, yeah, that was the end of the movie, but not the end of the story, because immediately that day, Edgar Courtwright, then the director of NASA Langley Research Center, was handed this directive to form a review board and investigate and document the cause of this major mission failure. So that review board was convened, included other members, distinguished members of the aerospace community, including Neil Armstrong, Hans Mark, then director of NASA Ames. Shout out to NASA Ames. There might be some people out there. The results of the review board were done and presented to Congress in June. Pretty incredible. So everything we're going to talk about here in terms of what happened to that oxygen tank to cause it to fail, done in 2 months. Corrective actions made. An Apollo 14 mission meant to launch in October is delayed only until January. So very, very incredible work. So let's talk about what the review board found. So it's very immediately obvious that something had happened, an event had happened with oxygen tank number 2. 2 things took place to narrow down what that root cause was. First, there's a great deal of history, material history on that tank. Talk about that. And then there was a good deal of laboratory testing that took place at the NASA centers. And without a doubt, that identified the problem that had taken place on that tank in Apollo 13. So, now we're going to talk a little bit about this, one of these tanks, the actual construction and how it works. Once again, I'm going to simplify. Simplification, not too gross. You'll see here that in actuality, the fans are are located in a slightly different place, and there's two of them. I'm going to show one, but for the most part, everything I'm going to show is technically accurate. So here is an oxygen tank in cross section. About 25 inches in diameter, double shell, very thin Inconel. Very thin Inconel, and there's a vacuum between these two shells of Inconel. This thing is like the ultimate Yeti cooler. Supposedly, you can fill this thing with ice, solid ice, just below freezing, put it in a 70-degree room, and the ice would not melt completely for 8 years. Now that is some good insulation going on right there. Once again, 300 pounds of oxygen stored about 900 pounds per square inch in a supercritical state. Supercritical state that enables lots of oxygen to be stored in a small volume. It's kind of a slush. It's not a liquid, it's not a gas, or it's not a solid. It's kind of everything mixed together. So we got to get oxygen into the tank, so we got a supply tube. Wait a minute, correct that. I said that wrong. I'm sorry. We got to get oxygen into the tank, so that is the purpose of the fill tube over here on the right. We get oxygen into the tank. Now, while we're filling oxygen in the tank, gas is going to build up here, and in order to keep on filling, we need to vent that gas out. So we have a vent tube. Now both of these tubes are connected at the side of the service module bay, and there's a fitting that gets ultimately shut prior to launch. Supply tube. The purpose of supply tube, that goes to the environmental control system and to the fuel cells like we saw in past diagrams. Now there is an electrical supply fitting here that provides passage of wiring that powers fans and a heater. And we'll talk about those right now. So we have a heater. Purpose of the heater is to maintain the pressure in the tank. Keep the pressure up. The way to keep the pressure up is you heat the tank up. In the supercritical state, you raise the temperature, you raise the pressure. Now, we need to know the capacity, the amount of oxygen in the tank, and to do that we have this capacitance tube. So essentially it's a tube, an outer tube that goes around the fill tube, and it forms a sort of physics 101 thing here, a cylindrical capacitor, and the capacitance of that capacitor is directly proportional to the amount of oxygen in the tank, i.e. the dielectric constant. So that dielectric constant tells you the capacity inside the tank. Now, there has been a concern that stratification would occur in 0G without any convection and result in anomalous capacity readings as well as pressure control. That's the purpose of these fans, to stir up the contents of the tanks. So that's why we have two fans, is to stir up the contents. Now you see one other electrical component here that becomes important. This thermostatic switch. That switch is there for a safety function. The tanks are designed such that a safety limit, a very conservative safety limit of 80 degrees is imposed in those tanks. And you want to weigh if the temperature gets above 80 with the heaters on, which really isn't going to happen in flight because of that very cold oxygen being in the tanks. This could only be something that could happen on the ground. Temperature gets above 80 degrees, that thermostatic switch is designed to open and interrupt power to the heater so that the temperature does no longer get warmer and overheat the tank. So, what did the review board find? First thing they found, wow, this tank had an interesting history. This tank and its companion, oxygen tank number 1, were actually first installed on Apollo 10 in the service module of Apollo 10 back in 1968, almost 2 years before the Apollo 13 mission. Now, they were taken out of that tank, or taken out of that spacecraft, for an engineering changeout. And during removal from the service module, they were, quote unquote, dropped 2 inches. Now, this is not as if they were being carried around and dropped to the floor 2 inches. We'll talk about what this dropping incident was here in a second. So, first of all, why this engineering change? I have there in those red circles on each one of these tanks is a component known as a back ion pump. And it turns out that there was an phenomenon at higher altitudes known as corona discharge that could take place, resulting in electromagnetic interference. Bottom line is they needed an engineering change to correct that problem. So an engineering change had been conducted on a set of tanks. They pull those tanks out of Apollo 10. They swap in the new tanks with engineering change. And that's the reason those tanks are no longer in Apollo 13. Now, let's talk about this dropping incident. The dropping incident. So here you see a sling and hoist mechanism that can be used to remove hydrogen tanks, can be used to remove oxygen tanks or fuel cells. We'll talk about the case of actually removing the oxygen tanks. So this connects up here to a crane in the high bay for removal of tanks and reactant valves. So in this situation, we're taking them out of Apollo 10 service module, and the first thing we have to do, you take the entire assembly out on this shelf. So the tanks are attached to a shelf. You take the entire shelf out. Well, the shelf is bolted down into the service module, so you have to take the bolts out. Well, that's what they did, except they left one bolt in right here. So you start to lift up, what happens? This thing begins to rotate about that point right there. Cantilever action. It rotates up. This tank actually contacts the shelf above. That dynamic load, this hoist mechanism actually has a flaw here. It cracks, breaks, and the tank shelf falls back down that 2 inches. That's what that dropping incident is about. So, back ion pumps are changed out, and this shelf is then reinstalled in Apollo 13. Now you may be saying, wait, whoa. We just dropped tanks that are going to fly on a manned spacecraft mission. What was done to make sure that everything was okay? Well, took this seriously, did an external inspection, appeared to be nothing significant wrong with the tanks. They actually pressurized the tanks. The tanks held pressure, no leakage. And the Failure Review Board blessed them off, and the tanks reinstalled in Apollo 13. Nothing else of significance is noticed until just weeks before the launch of Apollo 13 in the history of these tanks. And it occurs merely weeks before launch. March 16th, 1970. It's a day that a countdown demonstration test takes place. A countdown demonstration test, you suit up, you tank up, you take the clock down to 0 as if you're going to launch, except you don't launch. So, like I said, you fill up all the tanks, including the oxygen tanks and the hydrogen tanks in the service module. So there comes a point when the demonstration test is over, you're going to be sitting around a while, and you drain all the tanks waiting for launch day. Tank number 1 drains normally, as have all other tanks on all other Apollo missions. For the first time, oxygen tank number 2 will not detank using the normal procedure, the normal way of getting the contents out. So let's talk about how you get those contents out, both normally and then using a special detanking procedure that was used the night of March 27th going into early morning of March 28th. So how do you normally get the contents of a tank out when you're on the ground? What you do is you basically, it's a reverse process of filling the tanks up. You apply pressure to the vent tube. This pressurizes the tank, forcing the supercritical contents through the bottom of the fill tube and out to an oxygen dump. So, oxygen tank number 2, it doesn't work. Talk about why it didn't work. Now we're going to look at this portion of the tank in a little bit more detail. A little bit more detail, a little bit more complex. So here we see a vent line, a filter, pressurize the tank. Here's the fill line. Contents come up, and you see this little dogleg portion here and these fittings right here. Well, it turns out that, and it was suspected, because the tolerance, design tolerance of these fittings is such that a gap can exist between the fill line and this little barrier right here in the tank, creating a gap. Now, at no point was the dropping incident discussed as a possible cause for this fitting to be loosened right here. Now you try to fill or vent, empty the tank, you pressurize, that gas is immediately going to leak right through that gap and out. So you can't get the supercritical stuff up through the bottom. That's why the tank won't detank using the normal procedure. So what do they decide to do? Pretty smart thing. Look, if you turn the heater on, you're basically going to boil the contents out. The gas is going to come up through that gap and go out the fill line, and problem solved. So they develop a procedure for this detanking event. Basically, the technicians are told, do not allow the tank temperature to get above 80, otherwise monitor the detanking event and report back. Now, there's a little issue here. And that issue is that the temperature transducer, which provides temperature indications to the technicians, its limit, upper limit, is 80 degrees. Once it gets above 80 degrees, it provides no new information. It pegs out. And you can see here, over time, through that mid-watch, on the night of March 27th going into March 28th, that history getting up to 80, and she's steady as she goes, because that's the limit of the temperature transducer. So the heater remains on for 8 continuous hours. All the contents, yep, they boiled out just fine. Guess what? You do the thermodynamics calculation, and what you find is 8 continuous hours with that amount of oxygen as a function of time. Temperature in the tank can get up to 1,000 degrees Fahrenheit. In that situation, the wiring, internal wiring, Teflon coated wiring can crack and oxidize, exposing bare leads of the wiring to fans and heaters in the system. But wait, you should be saying, that thermostatic switch, it was designed, you said it was designed to open at 80 degrees just for a situation just like this. Why didn't the thermostatic switch open? Well, guess what it did? A little bit of history on the tanks and that switch. So these tanks were originally designed starting way back in 1962 by Beech Aircraft, who got the subcontract from North American to manufacture those tanks. Now, in 65, they were instructed to re-rate all the electrical components in the tank, not for 28-volt spacecraft power, but for 65-volt launch base power. 65 volts, value of that is to accelerate certain testing and have a higher voltage for that accelerated testing. Now, all the parts in that tank were re-rated for that higher voltage, except for the thermostatic switch. So, yea, verily, you can apply 65 volts to that switch, but the switch was never tested to open under 65 volts. So, on that night of March 27th into the 28th, the tank temperature rises up, gets above 80 degrees, and under 65 volts, arcing occurs. The thermostatic leads inside become molten and literally weld shut, allowing now continuous power to the heater. So, here we are, the day of launch. Oxygen tank number 2. The fill line is loosened. That is not a flight safety issue. That fill line is capped off. Nothing is going to happen with the contents of the tank due to that gap in the fill line. But it was part of the problem. The thermostatic switch is welded shut. Tank temperature is really cold now, never going to get up to that 80 degrees, and it's not going to require operation of that thermostatic switch. But another part of the problem in this chain of events that took place to lead to that fan wiring being exposed. So, the fan wiring is exposed. On that night, after the TV broadcast, Jack Loosma, the Capcom, said, "We'd like you to stir your cryo tanks." Jack Swigert complies. He flips the switch. A spark occurs across those bare leads. Turns out that Teflon insulation burns very well in this pressurized oxygen environment. That flame progresses along, gets to the pressure fitting for the wiring, weakens it. It bursts out into the dome. The dome itself has a burst disc that blows out at 80 psi, and there go the contents of the tank with explosive force. So, service module burns up in the atmosphere. How do you know this? Well, folks at NASA took great strides to recreate those events that took place in that tank using a variety of testing. So let's go look at some of those tests that they conducted. Here is a test that provides visual evidence of that Teflon coated wiring in that pressurized oxygen environment burning. Now this is a 1G environment. They also took pains to actually perform a drop test in a Langley drop tower to show that the same thing happens just a little slower under 0G. Tank weakens and then bursts out. Now the next test is the final conclusive verification of a problem that occurred. Guys down at JSC take a actual oxygen tank. They expose it to the same conditions as oxygen tank number 2. And they create the flame in the tank. This is in a thermal vacuum chamber to recreate the conditions in space. And you can see the results. Now, by the way, what took place was, as I said before, that event rapidly pressurizing the service module bay number 4. A small fire takes place, and then the panel actually separates on the service module, as you can see here. So, and by the way, there is that fuse thermostatic switch with about 50 volts, not 65, but a mere 50 applied. So I joked a bit about those 13s, implying that this mission was unlucky from the get-go. Was it an unlucky mission? Well, not when we consider when that tank actually failed. That was not the first time for a tankster. That actually happened to be the 5th time for a tankster. The 5th time creating just the right conditions, whether those were a function of actual tank contents, pressure, the actual orientation inside of the wiring. Nonetheless, the 5th time was when that flame was ignited and traveled up to the conduit, resulting in the failure of tank 2. Now, typically it's been said that the periodicity of those tanksters is about once every 24 hours. And in this case, on Apollo 13, there have been some anomalous pressure readings that increased the periodicity to that. If they had actually gone with that every 24-hour tank stirring process, the 5th stir would have taken place when Jim Lovell and Fred Hayes were on the lunar surface, in which case they would not have gotten back in time within 2 hours to use the command module or to rendezvous with the command module and to get back to Earth safely. So really a very fortunate set of events that that tank exploded when it did. Had it taken place after the astronauts had returned, the lunar module would have undocked and been trashed to the lunar surface for, again, seismic experiments. Again, too far away from Earth to use the contents, consumables inside the command module and service module to make it back safely. And likewise, if it had happened earlier, not enough power in the lunar module to get back safely, as we saw. So really, really a fortunate set of circumstances. So with that, look, 50 years since an incredibly heroic team came together. Both 3 astronauts, a 4th astronaut, the original member of the crew, steely-eyed missilemen down at JSC, industry partners all over the country came together to pull off this rescue. So our hats off to them. Thank you for being here tonight. I'm somewhat amazed that all this technology, which took me about a week to figure out, worked. So that's a relief. It's good to see so many friends here on the chat. And if you have any questions, I'll stand by for a few minutes and try to answer them, but just a few. Thank you very much for being here tonight, and please be safe. Thank you.